Welcome to the Deep Dive. So if you've been keeping tabs on the tech world lately, you've probably heard this story, right? This kind of big showdown. Edge AI versus cloud AI.
Oh, yeah. That narrative was everywhere.
Exactly. This constant debate about, which one's going to take over, which architecture will dominate everything, who wins.
And look, the analysis we've been digging into, it basically calls that whole debate a false premise. Kind of a distraction, really.
Totally. It missed the real story, which is much more interesting and, frankly, more powerful.
Right. So that's why we're here today, to cut through that noise.
Because the truth, and the industry is really catching on to this now, is that edge and cloud, they're not fighters in a ring. They're partners.
Yeah, a necessary partnership, complementary strength.
Destined for this unified approach, what we're calling the Converged AI Model. And this convergence, this partnership, is what's unlocking, genuinely unprecedented value across almost every industry you can think of.
Our goal here is really to give you that strategic shortcut, to help you understand this new setup because it is the new standard.
We're pulling out the key insights from some deep analysis on how this hybrid thing actually works. Not just definitions, but the mechanics,
Exactly. How do you intelligently split the work? What happens locally on the edge device versus what happens in the big centralized cloud? It's a dynamic thing.
The training, the decision-making, the data storage, it's all distributed.
Intelligently distributed.
So if you're, say, building a business strategy around AI, or maybe you're just really curious about how this distributed intelligence stuff is going to reshape things.
Which it absolutely is.
Then you'll want to stick with us. We're going to break down the core components, look at the feedback loop that makes them work together.
Dive into some really critical real-world examples.
And importantly, we're going to talk about the challenges, because it's not easy. The technical hurdles you have to overcome to make this work.
Okay, let's get into it. Let's unpack this architecture.
Right. So to really get why convergence is, essential, you first have to understand the pieces on their own. Their strengths, sure, but also their limitations. These are the pillars.
Makes sense. Let's start with the one closest to the action, right? The frontline worker. Edge AI.
Good place to start. Pillar 1. Edge AI, the power of local intelligence. So when we talk about edge AI, what we mean is running these, pretty sophisticated machine learning models.
Like neural networks and things.
Exactly, things like that. Running them directly on the local device.
Okay, so local device could be
what?
Like a sensor, a camera.
Doors, cameras, maybe a little industrial controller, systems embedded in machinery, even tiny microcontrollers in, say, a smartwatch. The point is, the processing happens right there, at the edge of the network where the data is actually born.
Okay, and why is that closeness, that locality so important, especially when everything seemed to be moving towards the cloud for years? Well, the benefits are huge, and often they're just non-negotiable for anything critical. First big one, low latency. Speed, pure speed, because you cut out the round trip. No sending data to some remote server, waiting for it to process, waiting for the answer to come back. You eliminate that delay entirely.
And for some things, even a tiny delay is too much.
Absolutely. Even, say, 100 milliseconds can be the difference between success and, disaster.
Yeah, the sources really hammer this home with examples like robots on an assembly line. Right. Or the classic one, self-driving cars.
Exactly. Autonomous vehicles. You just cannot wait for the cloud to tell the car to brake or swerve. It has to happen now, locally.
So Edge AI gives you that instant reaction, that responsiveness.
It's the foundation of responsiveness. And the second major strength, and this is becoming a huge factor in decisions now, is enhanced data privacy.
Ah, okay. Because the data stays put.
Precisely. If you've got sensitive stuff, maybe high-res video, patient health records, secret industrial process data, keeping it on site dramatically cuts the risk of exposure.
You're not sending it over the network where it could potentially be intercepted.
Right. You eliminate the biggest vulnerability, data in transit.
So for industries like finance, healthcare, places with tight regulations, or even just, say, facial recognition in a store, keeping it local is often the only way to go.
It makes compliance and risk management much, much easier. Edge AI is focused, it's fast, and it's private.
Okay, that's the edge. Focused, fast, private. Now, the other side of the coin.
Right, the counterpoint. If Edge is the nimble agent in the field, Cloud AI is like the central command, the HQ.
Pillar 2, Cloud AI, the foundation of scale. This is where the sheer horsepower lives, right?
Yeah, the almost unlimited computing power. Cloud AI means tapping into these massive centralized resources in huge data centers accessed over the internet.
And its strengths are basically the opposite of the edge's weaknesses.
Pretty much. It's the necessary inverse. It's not built for instant speed or local privacy, first and foremost. It's built for, well, brute force and capacity.
Right.
The number one strength is elastic scalability.
Meaning you can ramp up or down as needed.
Instantly. If your data load suddenly explodes, or you need to tackle some massive project needing petabytes of storage and thousands of processor cores, the cloud gives you that on demand. It scales up, scales down.
Yeah, try replicating that in your own building. It's practically impossible for most organizations.
Exactly. And tied to that is centralized management. The cloud just makes it easier to handle everything related to data, storage, keeping track of versions, managing access, refining those huge data sets you collect from all your edge devices.
It's the one place to manage all that data.
The single source of truth. Yeah.
Okay, so if the edge is doing the quick local decisions, what's the really heavy lifting that only the cloud can handle? What justifies that massive scale?
It's the stuff that needs enormous resources and takes time. Primarily, model training.
Teaching the AI in the first place.
Exactly. Training those complex models, especially the really big ones like foundational models or large language models, LLMs, that takes colossal computing power. We're talking weeks, maybe months, running on thousands of specialized chips like GPUs.
Right. No little edge device is going to do that.
Not a chance. And beyond just the initial training, the cloud is essential for the deep dives, the analytics.
Looking at the big picture over time.
Precisely. It performs deep historical analytics. You gather data, maybe filtered data, from thousands, maybe millions of edge devices over months or years. You bring it together in the cloud.
And that's where you find the subtle stuff.
That's where you run complex analysis to find patterns, weird correlations, subtle anomalies that no single device looking at its own little world could ever spot. The cloud is the brain driving the whole system's evolution.
Okay, so stepping back, you can really see the limits of each one on its own.
Yeah, becomes obvious.
A self-driving car trying to run purely on the cloud. Useless because of the lag.
Instantly obsolete, yeah.
And a big company trying to train a new global AI model using only its edge devices. Just impossible. Not enough power.
And that's the pivot point. That's why the industry realized the standalone approaches hit a wall. The edge doesn't have the resources. The cloud has latency and data transfer issues. They need each other.
So convergence isn't just a nice to have.
No, our analysis really emphasizes this. It's a technical necessity. It's the only way to build systems that are truly smart, responsive, and resilient enough for the real world.
Okay, so we understand the pillars. Now let's get into the interesting bit. How they actually dance together. This convergence thing, it's not just hooking them up, right? It's a deliberate strategy.
Highly engineered, yeah. It's all about intelligent task distribution. And the core engine driving this is what the sources call the fundamental feedback loop.
The feedback loop. Okay, break that down for us.
It's the heart of how the system stays smart and keeps getting smarter. The simplest way to put it is training in the cloud, inferencing at the edge.
Right. So start in the cloud. That's where the heavy lifting happens. The models need huge amounts of data, huge amounts of computing power to learn. That initial intense learning phase. All cloud.
That's where the model kind of learns about the whole world, not just, one specific sensor's view.
Okay, model trained in the cloud. Then what?
Then, once it's trained, validated, and this is key, optimized for size and efficiency. We'll talk more about optimization later.
Okay.
It gets deployed, pushed out to the edge device.
And that's where the inferencing part comes in.
Exactly. The edge device now has this trained intelligence on board. It uses the data its own sensors are collecting right now to make instant predictions or decisions. That's inference.
Okay, so cloud trains, edge decides. But you called it a loop. How does it loop back?
Good question. Because the edge device isn't just deciding, it's also experiencing the real world. It's collecting new data. Data that reflects what's happening now, maybe subtle changes, new situations, weird anomalies.
Stuff the original training data didn't perfectly cover.
Precisely. And that new data is gold for making the model better, for continuous improvement.
So does it just send everything back to the cloud? That sounds like a lot of data again.
And that's where the intelligence of the architecture comes in. No, it usually doesn't send all the raw data back. That would defeat the point, right? Undermine the latency and bandwidth benefits.
Right.
Instead, it typically sends back filtered data, or maybe anonymized data, sometimes just metadata, like anomaly detected at this time, or maybe only the short video clip of the anomaly.
High-value stuff only.
High-value, relevant field data. That gets sent back to the cloud.
And the cloud uses that too.
to retrain or fine-tune the model, update its knowledge based on this new real-world input, and then that improved model gets sent back out to the edge devices.
Completing the loop.
Completing the loop, often done overnight or during low usage periods. It creates this continuous cycle of improvement. The AI doesn't get stale. It keeps learning.
Okay, that makes sense. A self-improving system. And this constant loop, this back and forth, it must tie into the next point, right? Optimizing for performance and cost.
Directly. This strategic split of tasks is where you really unlock the efficiency.
Because let's face it, cloud computing isn't free, and neither is moving massive amounts of data around. That's a huge cost center for businesses.
A major one. And the savings here can be enormous by letting the edge devices handle those immediate low latency tasks. The basic detection, filtering, quick predictions, you fundamentally change the cost equation.
How so?
You drastically cut down the sheer volume of raw, unprocessed data that needs to be shipped off to the cloud. Think about bandwidth costs, data transfer fees. They plummet.
Right. So using that camera example again, instead of streaming 247 video from thousands of cameras, you're maybe just sending small alerts or summaries.
Exactly. Maybe just a tag saying, person detected zone 3, 2.15 p.m. The difference in data volume and therefore cost is often orders of magnitude.
Okay, so Edge handles the cheap, fast stuff locally.
And the cloud is then reserved for what it does best, but what's also expensive. The really heavy data guzzling tasks. Foundational model training, large-scale historical analysis.
You're using the expensive cloud resources optimally, only for the high-value number crunching.
Exactly. And at the same time, you're not overwhelming the edge devices. They have limited power, remember. You keep them focused on what they can do efficiently. It's just a much more cost-effective, tiered way to build the system.
Makes sense. Now, we can't really talk about this edge-cloud partnership becoming practical without mentioning the tech that, well, enabled it, right? 5G and IoT.
Absolutely essential. The catalysts, you can't separate them. Edge, cloud, IoT, 5G, they're all interlinked now.
Let's start with IoT, the Internet of Things.
Right. IoT devices, the sensors, the cameras, the smart meters, all those physical things, they are the source of the data flood. They generate the sheer volume that makes this whole converged model both necessary and possible. They're the eyes and ears.
They create the raw input. Edge AI needs that input to do its local filtering and processing.
And cloud AI needs the aggregate of that filtered input from many IoT devices to do its deep learning and big picture analysis.
So without IoT, the whole AI system basically starves for data.
Pretty much. And then there's 5G. That's the super fast highway connecting the edge and the cloud.
And it's not just about faster downloads, is it? The sources emphasize other aspects.
No, it's much more than just speed. Critically, 5G offers dramatically lower latency over the air and is built to handle way more simultaneous connections, essential for massive IoT deployments.
So that low latency in 5G is key to making that feedback loop actually work in near real time.
Precisely. It means those updated models from the cloud can get pushed out to the edge devices quickly and reliably. Those over-the-air updates are vital for managing a distributed system.
Right.
And 5G has other tricks, like network slicing. This lets organizations carve out dedicated, high-priority lanes on the network just for their critical edge applications.
So you can guarantee performance for, say, factory robots or remote medical equipment.
Exactly. Guaranteed responsiveness and reliability. Without 5G providing that fast, reliable, low-latency connection, and without IoT generating the data, the hybrid model, it would just be a nice idea on paper. These technologies made convergence a reality.
Okay, this is great. We've got the theory, the mechanics, but let's make it concrete. Because this converged model, it's not science fiction anymore. It's out there doing real work.
Absolutely. Let's start with maybe the most dramatic example, the one that really highlights that need for speed. Autonomous vehicles.
Use case 1, autonomous vehicles, on-road decisions, off-road updates. Yeah, you can't get much more high stakes than that.
Right. So the edge function is obviously the car's own onboard computers, packed with processors.
Doing the driving, basically.
Doing the immediate driving decisions, braking hard, steering to avoid something, figuring out exactly where that pedestrian is going, all based on instant data from its cameras, its radar, its LiDAR sensors.
And latency there is just zero tolerance.
Zero tolerance. Any delay is catastrophic. This local edge AI is the pilot, flying the plane, using its optimized model to keep everyone safe right now.
Like you said, can't phone home to the cloud, as permission to hit the brakes.
Exactly. But the cloud function is what makes that pilot smarter over time. All the data the car collects, successful trips, tricky intersections it navigated, weird sensor readings it encountered.
Billions of miles driven by the whole fleet.
Exactly. That data, often anonymized and summarized, gets sent up to the cloud.
And that's where the massive scale comes in handy again.
Right. In the cloud, data centers analyze data from thousands, maybe millions of vehicles. They look for patterns, rare edge cases, ways to improve the driving algorithms system-wide.
They learn from everyone's experience.
They retrain those core AI models with all this new knowledge, and then those improved models get deployed back down to the entire fleet, usually through those over-the-air OTA updates.
So the car literally gets smarter overnight.
That's the idea. It learns from the collective global experience, not just its own driving. So, edge for immediate safety, cloud for long-term intelligence. They're completely dependent on each other.
Okay, fascinating. Let's shift scale now. From a single car to a whole city. Smart cities.
Use case 2, smart cities, local monitoring, centralized management. Yeah, think about a big city. You could easily have hundreds of thousands of connected things, cameras, traffic sensors, grid controllers.
And the big problem there, as we touched on, is just the sheer volume and cost of moving all that data. Streaming video from every traffic light 24/7, forget it.
Exactly. The budget would explode. And that's where Edge AI comes in again.
On the camera itself.
Right, or on a nearby sensor hub. The AI runs locally. It watches the video feed right there and does the immediate tasks. It detects an accident instantly, sees traffic backing up and maybe flags it, analyzes pedestrian flow to adjust traffic light timing.
So it deals with the local situation fast.
And crucially, it avoids streaming all that raw, potentially sensitive video data back to a central server all the time. That helps with privacy, and it delivers a much faster response to, a fender bender.
Okay, Edge handles the immediate stuff. What does the cloud do for the city?
The cloud takes the strategic view. It aggregates the outputs from all those edge devices, the alerts, the summaries, the statistics, maybe heat maps of activity.
So not the raw video, but the insights generated at the edge.
Exactly. It pulls all that together from across the entire city, and then it runs the big analyses to spot long-term trends. Where does traffic consistently bottleneck? How does weather impact energy use across neighborhoods? Where do we need more crosswalks based on pedestrian data over months?
So it helps with the big citywide planning decisions.
That's the role. Strategic planning, resource allocation. Edge handles the tactical, minute-by-minute stuff. Cloud handles the long-term strategic vision.
Okay, one more. Let's go industrial. Manufacturing. Predictive maintenance, where downtime is a killer.
Use case 3. Manufacturing and predictive maintenance. Oh yeah, this is a classic textbook converged model application. Downtime can cost millions per hour in some plants.
So how does it work there? Edge first.
Edge function means putting sensors, sometimes even sophisticated digital twins, right onto critical machines. Robotic arms, pumps, motors, presses.
What are they monitoring?
Things like vibration, temperature, how much electricity it's drawing, even the sounds the machine makes. Really granular, real-time data, often sampled many times a second.
And the Edge AI is watching that stream constantly.
Constantly, looking for tiny deviations from normal. Let's say it detects a specific vibration frequency starting to spike something its model knows often precedes a bearing failure.
What happens then? Does it call the cloud?
Not necessarily right away. It might instantly flag that specific machine for inspection, maybe even trigger a controlled shutdown of that part of the line if the anomaly is critical. The key is immediate local detection to prevent a catastrophic failure right now.
Prevents the big, expensive breakdown.
Avoids that unplanned, costly downtime. That's the immediate edge benefit.
Okay, so Edge is the immediate firefighter. What's the cloud's role in the factory?
The cloud provides the foresight, the predictive power. The edge sends its diagnostic data, the anomaly flags, usage logs, up to the cloud.
Along with data from maybe hundreds of similar machines in other factories?
Exactly. The cloud aggregates all that data. And that's where the really powerful analysis happens. They build much more accurate predictive maintenance models that can correlate those subtle early warning signs with actual historical failure data.
So it goes beyond just something's wrong to...
Based on this specific vibration pattern and usage history, this bearing has an 85% chance of failing within the next 60 days.
Wow. Okay, that's a game changer.
It really is. It lets them schedule maintenance proactively during planned downtime, order the parts in advance. It turns maintenance from a reactive scramble into a precise planned operation. Huge cost savings, much better efficiency.
So across all these cars, cities, factories, it's the same pattern, isn't it?
Fundamentally, yes.
Edge for the immediate, the urgent, the latency sensitive, the cost-critical local stuff. Cloud for the deep learning, the big picture context, the evolution, making the whole system smarter over time.
Right. So that really brings us to the why. Why should organizations, why should you listening really care about embracing this converged strategy? What are the big strategic payoffs?
Yeah, beyond just the tech working, the strategic advantages are pretty compelling. We can boil it down to about 5 key benefits. First, the one we keep coming back to, low latency and real-time decision-making.
Table stakes for anything interacting with the physical world.
Absolutely. For many systems, speed isn't just nice, it's the fundamental requirement for it to even function safely or effectively.
Okay, benefit 1, speed. What's next?
Second, and this is climbing the priority list everywhere, enhanced privacy and security.
Because the data stays local more often.
Exactly. Processing sensitive stuff right there at the edge. It helps meet data residency rules, GDPR, things like that. And it just drastically reduces the risk profile compared to constantly shipping raw data across networks.
Yeah.
Minimizes the attack surface in a way.
In a big way. Okay, third benefit, scalability and flexibility.
How so? Seems like you get the best of both worlds.
Kind of, yeah. You get the agility and instant response of the edge for your immediate operational needs.
Yeah.
But you still have the cloud's basically limitless resources backing you up for growth, for storing huge historical data sets, for training ever bigger models down the line.
So the architecture itself doesn't become a bottleneck as you grow.
It's much less likely to. It's designed to scale both locally and centrally. Fourth benefit, and this one hits the bottom line directly, cost efficiency.
We talked about this with task distribution. Less data transfer, smarter use of cloud compute.
Exactly. Those savings on bandwidth and cloud processing fees can be massive, especially at scale. By only sending the essential, maybe pre-processed data to the cloud, you optimize your operational spending significantly.
Makes sense. And the last one?
The fifth one, and this is huge for industrial settings, manufacturing, utilities, operational reliability.
Meaning it keeps working even if the internet goes down.
Precisely. Edge devices are typically designed to run autonomously. If the connection to the cloud gets cut, maybe a network outage, maybe it's just a remote site with spotty connection, the essential functions, the safety critical stuff running on the edge keeps operating.
So the factory doesn't just grind to a halt.
Exactly. It provides resilience, business continuity. The system isn't brittle. It doesn't have that single point of failure dependence on the cloud connection for core operations.
Okay, that's a really strong list of advantages. Speed, privacy, scalability, cost, reliability.
Yeah.
But it sounds complex. Nothing this powerful comes easy, right? There have to be challenges.
Oh, absolutely. Implementing this is not trivial. We definitely need to talk about navigating the challenges of integration.
Where do we start? What's the biggest headache?
Probably the sheer complexity of managing it all. Challenge 1, management and orchestration.
Right. It's not like managing servers in one data center anymore. You've potentially got thousands, millions of devices scattered everywhere.
Exactly. Devices spread across different locations, maybe different countries, often in places that are hard to get to, maybe running different hardware. It's a management nightmare if you don't have the right tools.
So what do you need?
You need robust, centralized platforms specifically designed for this. Orchestration platforms. They're essential for handling things like, how do you securely get a new device online without someone physically touching it? It's called zero-touch provisioning.
Well,
How do you push out those critical model updates to the entire fleet reliably? How do you monitor the health of all those devices remotely? How do you make sure every single one gets security patches instantly?
without sending engineers out to every lamppost or factory floor.
Precisely. And these management tools, they need to be comprehensive,
Right.
covering device setup, data handling, visualizing what's going on. And this is crucial, according to the sources, making it easier to actually create the AI models that can run on all that diverse edge hardware.
Because the hardware itself isn't uniform.
Far from it. That's a killer complexity. Your orchestration layer has to deal with pushing models to tiny, low-power microcontrollers, but also to powerful edge gateways with specialized AI chips and everything in between.
So if an update works on 90% of devices, but fails on 10% because of hardware differences, that's a problem.
It's a huge problem. You've just created blind spots in your intelligence network. So managing that dispersed, diverse fleet, monumental engineering challenge.
Okay, challenge 1, management. What's next?
Yeah.
This ties into the models themselves, right? Challenge 2, model optimization.
Yeah, this is where the cloud genius meets the edge reality check.
The translation layer, you called it.
Exactly. Think about it. You train this amazing AI model in the cloud, unlimited power, maybe using high precision math like 32-bit numbers. It's big, it's powerful.
And then you need to cram it onto a tiny chip on the edge device.
A chip with limited memory, limited processing power, maybe running on a battery. That massive cloud model just won't fit, or it'll run way too slowly or drain the battery in minutes.
So it has to go on a diet, a serious diet. Optimization, compression. How does that actually work? What are the techniques?
There are a few key ones. A big one is quantization.
Computization.
Yeah, it means reducing the precision of the numbers the model uses. Instead of those high precision 32-bit floating point numbers for all the calculations,
You knock it down.
you knock it down, maybe to 8-bit integers, sometimes even further, like using binary values for certain things. This drastically shrinks the model size, the memory it needs, and makes the calculations much faster on simpler, energy-efficient edge hardware.
Hold on. If you reduce the precision, aren't you making the model dumber? Less accurate?
That is exactly the challenge. Yes, you are potentially sacrificing some accuracy, and that's the fine art of optimization. You have to compress the model enough to run well on the edge, but without losing so much accuracy that it becomes useless.
So it's a trade-off.
It's a critical trade-off. Techniques like pruning, removing less important connections in the neural network also help shrink the model. And sometimes they use knowledge distillation, where you train a smaller student model to mimic the behavior of the big, accurate teacher model from the cloud.
Trying to capture the essence without the bulk.
Exactly.
Yeah.
Finding that sweet spot between size, speed, power consumption, and accuracy. That's a continuous, really sophisticated engineering task. Getting optimization right is absolutely key to making the converged model work in practice.
Okay. Management optimization. What's the third big challenge? It has to be security, right?
Always. Challenge 3, security. And in this hybrid world, it's a double-edged sword, really. Dual vulnerability.
Because you have two different environments to protect.
Two fundamentally different attack surfaces. First, the edge devices themselves. Think about that sensor on the highway or a smart meter on the outside of a house. They're physically out there.
Vulnerable to someone just messing with them.
Yeah, physical tampering, theft. Also, more sophisticated attacks trying to extract the AI model or sensitive data directly from the device hardware side channel attacks. So you need strong on-device security, encryption, maybe physical tamper detection.
They're in the front line. But the cloud is still a target too, right? It holds the crown jewel.
Absolutely. The cloud environment needs its own super strict security. You're protecting potentially massive amounts of aggregated sensitive data, but you're also protecting those incredibly valuable pre-trained AI models.
Which represent a huge investment.
Millions of dollars, potentially years of R&D. They're a prime target for corporate espionage or attackers looking to understand or manipulate the AI's behavior. So if you fail to secure either the edge or the cloud properly, the whole system is compromised.
It demands a security strategy that covers everything end to end.
Holistic and integrated, yeah. It's a major undertaking.
Okay, so we've covered the what, the how, the why, and the this is hard. Let's look forward now.
Yeah.
Because this converged model, it's not static, right? It's evolving. What's next?
Yeah, it's definitely the baseline now, but new ideas are pushing it further, especially towards giving the edge more autonomy and building in privacy more deeply. Two big trends are really shaping that next phase.
Okay, what's the first one?
The first is the rise of agentic AI and federated learning.
Agentic AI sounds active. What does that mean for the edge device?
It means the edge device becomes more than just an inference engine blindly following cloud instructions. It gains more autonomy.
Like, it can think for itself more.
Sort of, yeah. It becomes capable of more complex decision-making locally. It can adapt to unexpected situations, maybe even figure out how to correct minor issues itself without needing to constantly check back with the cloud in real time.
So it's less of a puppet, more of an actual
Yeah.
agent operating out in the world.
Exactly. Managing complex tasks or workflows right there on the edge, that's a big shift, giving it more independence.
And that ties into the second part, federated learning. How does that fit?
It fits perfectly, especially with privacy concerns. Federated learning tackles that feedback loop challenge. How do you improve the central model without collecting everyone's sensitive raw data?
Right, the problem of sending private info back to the cloud.
With federated learning, the raw data stays on the local edge device. It never leaves. Maybe it's on your phone or inside a hospital's network.
Okay, so how does the main model get better then?
The model training happens collaboratively across many decentralized edge devices. Each device trains on its own local data, and then it only sends back the updates to the model, things like changes to the model weights or gradients.
Ah, so it shares the learning, not the data itself.
Precisely. The central model gets improved by the collective experience of all the edge devices, but without ever seeing the raw, private data from any single device.
That sounds huge for privacy-sensitive areas. Healthcare, finance.
It's a massive enabler. It allows continuous learning while preserving privacy at a fundamental level. It's a very powerful concept gaining a lot of traction.
Okay, so more autonomous, privacy-preserving edges. What's the second major trend you see?
The second is how this convergence is enabling a new era of human-machine collaboration. Pushing intelligence right to the point of interaction changes how we work with technology.
Give us some examples.
Well, think about AI-powered wearables, smartwatches, fitness trackers, maybe even augmented reality glasses in the future. The edge AI on the device itself processes complex sensor data, your heart rate variability, how you're walking, your sleep patterns.
And gives you feedback right away.
Yeah, immediate personalized insights and feedback, often without needing to constantly stream your raw biometric data to the cloud. That makes it faster, more useful, and people trust it more if the data stays local.
Okay, wearables. What about in industry?
The sources point strongly towards things like collaborative robots, cobots in warehouses or on factory floors.
Robots working right alongside people.
Exactly. The edge AI is critical there for the robot's real-time navigation, making sure it spots obstacles, including humans, and interacts safely and efficiently in a dynamic environment. That low-latency local processing is essential for safety.
And the cloud's role in this collaborative future, does it become less important?
Not less important, but maybe its role shifts slightly. It becomes more like the central brain or the conductor of the orchestra. It's not micromanaging every single note or movement.
Because the edge agents are smarter now.
Right. But the cloud ensures the whole ecosystem, all the wearables, the robots, the factory controllers, the smart infrastructure stays coordinated. It aggregates the high-level insights, pushes major updates, ensures everything works together cohesively, and learns from that collective intelligence.
So it's managing the overall intelligence system.
Exactly. Which really reinforces that core idea we started with. This really is the blueprint for the future.
The era of one dominant computing style mainframe, PC, pure cloud, it's over.
It's definitively over. The future belongs to this blended, harmonized architecture. Edge and cloud working as one dynamic, adaptive system.
And it's more than just a technical fix for latency or bandwidth.
Yeah. The analysis frames it as the blueprint for building a world that's fundamentally more intelligent, more efficient, and more responsive. A world where you can have speed, scale, and privacy working together, not canceling each other out. #tag outro.
Wow, okay. That was definitely a deep dive and really necessary given how fast this is becoming the standard way of doing things. So if you're trying to pull this all together, the core idea to hold on to is that dynamic balance. The cloud gives you that massive scale, the ability to look at vast amounts of history, and it does the really heavy lifting of training the AI models.
With foundational learning.
Right. And the edge. That's all about low latency, keeping data private when needed, and doing the immediate real-time inference, the actual decision-making out in the physical world.
Keeping things running safely and efficiently second by second.
And we saw how powerful that is, whether it's a car making a split-second avoidance maneuver,
or a factory predicting machine failure weeks in advance,
or a city using aggregated data to plan smarter infrastructure. The impact is huge.
Transformative, really.
So the actionable takeaway here, for you listening, whether you're in business or just following the tech, the path forward really is hybrid.
No question.
You need to embrace this converged model. But more than that, you need to invest strategically. In the infrastructure, yes, but maybe even more importantly, in the skills.
Yeah, the expertise needed is different.
Especially in those tricky areas like model optimization, making cloud models run efficiently on the edge, and in mastering those complex orchestration platforms to manage the whole distributed system.
Getting good at that is going to define who leads in the next decade.
Okay, so to wrap up, we always like to leave you with a final provocative thought, some to chew on.
Right. We talked about that trend towards agentic AI. At the edge, these devices getting smarter, more autonomous, capable of self-correction even without talking to the cloud constantly.
Yeah, more independent.
So this converged model brings resilience, which is great. But think about the implications of that increasing autonomy. What happens when a critical edge device, maybe controlling infrastructure, maybe a vehicle makes a really high-stakes decision while it's operating offline on its own? How do we handle governance, accountability, our fundamental trust in that decentralized intelligence when the central brain isn't directly involved in the decision.
It really shifts the locus of trust, doesn't it? From the controlled server room.
Right down to that individual chip operating out there in the world. Something to think about.